Hello people, now we are going to discuss two questions. First question is from GATE 2015 exam. Second one is from GATE 2016 exam. Okay, both of these questions are almost identical. They are saying what is the minimum number of JK flip-flops required to implement a synchronous counter whose counting sequence is this. Okay, so whenever we want to determine minimum number of flip-flops required to implement a counter with some counting sequence, let's see what is the procedure. Say they have given you some counting sequence. Suppose this is the sequence that we want to implement. You just need to determine what is the minimum number of bits required to implement the biggest number. Biggest number here is 12. Okay. 12 can be represented in 4 bits. That means each and every number will be easily represented in 4 bits because we can represent biggest number using 4 bits. So your answer is 4. 4 flip-flops will be required to implement this counter. Okay. Look, if we have enough number of flip-flops to represent each digit in this counting sequence, we can easily implement a counter. See, for such a sequence, you can draw the table that we already discussed and we have solved multiple such questions. Present state, next state, and inputs required. Okay, you just draw the key map for inputs. You will get to know what is the combinational circuit here. Look, I'm not going into very detail of how to draw this, but the thing is there will be some common clock to all of these. Okay, to make them synchronous, there will be a combinational circuit which will take as input the current state. Okay, current state is defined by output of every flip-flop. So it will have these inputs, okay, like this. Now, say at any given time current state is 4. It will get to know that counter is in the state number 4. We can be very sure of the next state. See, after 4, next state is surely 8. After 8, the next state will be 12. If you are currently on 12, next state is 2. Okay, so at any given time, next state is known. That means we just need to define a combinational circuit such that it could generate output for each and every flip-flop. By saying that it could generate output, I mean its output must be generated in such a way that if that output is given as input to these flip-flops, suppose these are JK flip-flops, it will be generating J and K for each and every flip-flop. Okay, so 2 inputs here, similarly 2 inputs here, 2 here and 2 here. These values of J and K will be dependent on these outputs. Okay, and they will be generated in such a way that if current state is 1, next state will surely be 4. If current state is 4, next state will be 8. The thing is, if biggest number can be represented in 4 bits, 4 flip-flops are enough. That's it. Okay. Now, let's discuss about this sequence. Biggest number is 3. 3 can be represented in 2 bits. Some of you might think that 2 flip-flops are enough. Okay. Because every number in the sequence can be represented in 2 bits. Okay. But here, if I tell you the current state, you can just exactly tell me what is the next state. I'm saying current state is 4. You know next state has to be 8. That is, this machine, the machine that we are going to implement will be deterministic. But this sequence is not deterministic. There is some non-determinism in this sequence. If I tell you the current state, you are never sure what is the next state. I am saying current state is 1. What is next state? Just try to guess it. See, if current state is 1, next state can be 1. If current state is 1, next state can be 2. Okay. So you actually need to know which of these ones is the current state. If we are here, next state will be this one. If we are here, next state will be this one. Okay. So the summary is you need to distinguish between both of these symbols. You need to distinguish between both of these symbols, both of these and both of these. Okay. I agree that 2 bits are enough to represent all of these states. 0, 0, 1, 1, 2, 2, 3, 3. You can represent this sequence in 2 bits. But this combinational circuit needs to know the current state that will be given by output of these flip-flops. And we need to design this circuit in such a way that next state is already known to us. Okay. See, while designing this circuit, I'll be knowing on 0, next state is 1. So I'll generate these outputs in such a way that next state becomes 1. But while designing circuit for these two flip-flops, I don't know the next state only. Okay, so there is something to be done while designing this flip-flop so that I am able to distinguish between two common symbols, okay, or two similar symbols. One solution is, because we need to distinguish between two unique items only, why don't we fix one bit? So I'm saying there is a bit named A whose value is 0 for this 0 and 1 for this 0. Okay. Similarly, it is 0 here and 1 here. So I can distinguish between both of these ones. It is 0 here and 1 here, 0 here and 1 here. Now, between these two 2's, you can easily distinguish based on value of A. If I am saying current state is 2 and A is 0, you can easily say this one is the current state. Okay. That means you are here and next state can also be easily guessed. That will also be 2. Okay. 2 with A is equal to 1. Now, what you do, you design a counter for this counting sequence. Forget about this. Design a counter for this one. Here each and every number can be represented in 3 bits. That means 3 flip-flops are enough. See, the counter that we are now designing, its counting sequence is 0, 0, 4, 1, 5. Five, 2, 6, 3, 7. Just design this counter. Now, its biggest number in the sequence is 7. That means 3 flip-flops will be required. Okay. So, you just design a counter using 3 flip-flops. And what we are going to do is, we'll neglect the output of first flip-flop. Even though first flip-flop will be part of circuit, we'll completely neglect it. See, this counter can be implemented in this way. Okay, there is a clock signal and these outputs are generated and so on. What we are going to do is, to determine its current state, we will just neglect this flip-flop. Only these 2 bits will be taken. Now, if you neglect this column A, the required counter is implemented. See, actually, current state will be 0, 0, 0. But we will neglect this bit and we'll say current state is 0 only. Okay. After this state, actually current state will be 1, 0, 0. We are going to neglect it. We are saying after giving a clock also this remained 0 only. Okay. Then this one, so on. So the required counter is implemented with the 3 flip-flops. This flip-flop is part of circuit. Some of the students think this is not part of circuit, so still 2 are enough. What is the benefit of using this? This counter actually needs value of A. But we don't need value of A. The output that we want to see is only generated by these 2. Okay. So this is part of circuit. Its current value is used while generating the next input. But we only focus at these 2. Okay. So the minimum number of flip-flops for this is 3. Answer to the first question. The question from GATE 2015 is 3 JK flip-flops are required. Now let's see the question from GATE 2016. See, its counting sequence has non-determinism because we need to distinguish between these 3 symbols 0, 0, 0. If I tell you that current state is 0, you can never determine what is the next state. It could be possibly 1, possibly 2, or even 3 also. If current state is 0, if it's this one 0, then next state is 1. If it's this 0, next state is 2. If it's this 0, next state is 3. That means 2 plus 2 flip-flops are required. Your answer is 4. How did I get 4? See, biggest number is 3. So 2 flip-flops are required to represent each of these numbers. That means 0, 1, 2, 3. All of these numbers can be represented in 2 bits. Surely we will have 2 flip-flops. Okay. Now let's talk about non-determinism. There is a non-determinism. We actually need to distinguish between 3 similar symbols. Now to distinguish between 3 symbols, you need 2 bits. 1 bit is not enough. Okay. 1 bit can have only 2 values and hence it could distinguish between 2 similar items only. Here we need to distinguish between 3. That means 2 more flip-flops will be required. So your answer is 4. Answer to this question was 2 plus 1 is equal to 3. This is 2 plus 2 is equal to 4. Okay. Now let's just go into a bit more detail. See, current value is 0. Let's start from here. First state is 0. After this we want to go to 1, then again 0, then 2. 0, 1, 0, 2, 0, 3. Okay. So we want to design such a counter. Now we need to identify currently if the state is 0, it is which 0. For that I am reserving 2 bits called x and y. Let us say xy is 0, 0 for this 0, 0, 1 for this 0 and 1, 0 for this 0. Okay. And you'll say what is xy for this number and this number. We simply don't care. Okay. It is don't care. Take it anything. Just say it is cross, cross, cross. Or just fix a value. Say it is 1, 1, 1, 1 and 1, 1 here also. That's it. Okay. Now you design this counter. See, every number is represented in 4 bits. That means 4 flip-flops are required. And simply neglect the first 2 flip-flops while actually trying to guess what is the current state. Okay. So suppose we have used these 4 flip-flops. Now these 2 are the part of circuit. Their value is actually used to get to know the current state. Current state is of 4 bits. But while giving the output, we neglect these 2 and only these 2 are considered. Okay. See, you will generate a counter for 0, 13, 4. 0, 13, 4, 14, 8, 15. 4, 14, 8 and 15. Yeah, we are going to design this counter. But because we are neglecting first 2 bits, actually the output will be this. Okay. So I hope you understood these questions. Answers are 3 and 4. Okay.